Great, thanks for having me. My name's David Golightly. I'm a staff software engineer at MasterClass. I think it was Dylan earlier that mentioned how everybody who writes Effect writes the same kind of code. I'm gonna maybe challenge that assumption a little bit. I found some pretty unique patterns that I hope to share with you today, but this is who I am. I'm based out of the San Francisco Bay Area in the USA. And these are the things that I like. But I've been at MasterClass since 2021. So most of MasterClass is not what I'm about to show you. We have all the standard web stack stuff. We have a Rails backend, we have a React frontend, we have a Next.js app, all in conventional TypeScript, except for the Rails part, unfortunately. But we built a new thing recently and we shipped it. So I just want to go ahead and tell you about it. So it's a new product. It's called On Call, not to be confused with, when you get paged in the middle of the night. That's not what we're talking about here. This is a product that we call On Call that we sell to consumers. And the basic idea is, MasterClass, what we're famous for, we have a whole roster of world-renowned experts in their field. And we thought, what if, wouldn't it be great if you could talk to them? And so we built this product that lets you essentially talk to them. And we have worked closely hand in hand with all of our instructors not all of them have signed on necessarily yet, but we signed on a whole list of instructors who are coming over the next several months. We launched back in December with these two instructors, but we've already added Mark Cuban. We have Gordon Ramsay on the way. We have LeVar Burton for you Star Trek fans / Reading Rainbow fans. We have a whole list of MasterClass instructors that are coming to enrich this product, and you can talk to them and interact with them and ask them questions and advice about their area of expertise. So let's see if I can make it work. See this? Great.
Hey there, this is the AI of Dr. Matt Walker. How are you feeling today?
I'm a little bit jet lagged. I've had a long flight from the US. Do you have any advice for me?
Jet lag can be quite challenging. It's important to try to sync your internal clock with the local time as soon as possible. Exposing yourself to natural light during the day can help adjust your circadian rhythm.
What else can I do? What else can I do?
Staying hydrated and avoiding caffeine close to bedtime can also aid in adjusting to the new time zone. Additionally, trying to maintain a regular sleep schedule even while traveling can mitigate some effects of jet lag.
Well, that's useful. Thank you for the advice.
You're welcome. Safe travels and restful nights ahead.
So that's On Call. And as you can see here, I just had a conversation with Dr. Matt Walker, who's a sleep expert. On the right in the network panel, you see the WebSocket messages that were being sent back and forth. So our clients, our iOS and web clients, connect to a service that we call Cortex. And it's Cortex that I want to talk about today, because Cortex is our WebSocket server that is the orchestration layer behind On Call. So how does it basically work? So basically, after authenticating, clients connect to Cortex over a WebSocket connection. They get a signal from Cortex that it's ready to go. They start streaming audio to Cortex. Cortex passes that along to the STT, or speech to text service that randomly, or not randomly, but sometimes sporadically will generate transcriptions of what the user has said. We take the text of those transcriptions, we send it to an LLM that is specially trained for that instructor. And then that instructor generates a response. We send the response to a text-to-speech service that generates audio in that instructor's voice. And then we send the audio back to the browser or the iOS device where it's then played back. So this is the basic user experience loop of Cortex. 3 services, STT, speech-to-text, LLM, and TTS, text-to-speech. I'll be using those terms a lot. As you can see, Cortex provides clients with a kind of interface they can use in order to talk to these 3 different layers. The clients only talk to Cortex, but then Cortex delegates the functionality and does a sort of handoff, what we call it orchestration, with the backend services. So there are actually off-the-shelf services that do this today. And we tried some of them, but they didn't really suit our needs exactly. So what are those needs? We can think of Cortex as a glorified event pipeline. It doesn't really generate anything on its own. It doesn't own the LLM necessarily. It just takes events from the client and from other random services that it's connected to, and it passes them through, makes decisions about how to dispatch them, and then it ultimately sends them off to other services or back to the client. Of course, it's possible for anything to go wrong here at any point, so Effect is really good at that. As we know, the error channel is fantastic. The type safety really gives us a strong sense of security. We also need to understand what's going on under the hood. We need to know what our users are experiencing. Where is time being spent? Not necessarily in Cortex, but between the services that it's delegating to, that sometimes with third-party services, we don't actually have the ability to instrument them directly. And so implementing our own observability in Cortex was really valuable. And then last, this is, as you could guess, a pretty asynchronous app, and asynchronous apps tend to be complicated. There's a lot of events flying around, and so being able to wrangle all of those events and manage them and impose an architecture on them turned out to really simplify a lot of the complexity here. So we had never used Effect before. I had a little bit of experience with RxJS years ago, but I didn't really feel like it was going to be a good fit for this. But our engineering manager on the project had done a quick and dirty prototype of just WebSocket and event target-based implementation of Cortex early on. It was really impressive for a prototype. It was mostly created with the help of ChatGPT, but it still didn't quite work correctly. It dropped some things. It didn't really have good error handling. It wasn't really going to scale, and it didn't have the kind of responsiveness that we needed. So I got brought onto the project, and I started investigating, how are we going to architect this thing really? Around June of last year. In July, I found Effect, basically through Twitter, and a lot of the advocacy of folks who have been developing it, who have been experimenting with it. So if you feel like you're shouting into the void, just know that sometimes somebody's listening. And so I researched it, and I did some prototyping. I came up with an internal presentation. I presented it to the engineering team at MasterClass, and they said, yeah, this sounds like it would actually be a good fit. We're on board, go ahead. And so I got the go ahead. I started incrementally re-implementing parts of it, but quickly found out that in order to get the most value out of Effect, you really had to go all in. So by December or so, when we launched, the app was pretty much 100% Effect. Let's take a little bit more closer of a look at what exactly is going on here. So as we mentioned, Cortex is an orchestration layer that delegates to an SDT, an LLM, TTS. It doesn't have its own persistence layer. Instead, we have a Rails app that does more conventional, CRUD operations and so forth, and supports also a lot of user-facing and pre-paywall and payment and all of those sorts of things that the Rails apps usually do. But they also handle a lot of configuration and memory persistence that Cortex relies on. But this allows Cortex to be dedicated essentially to real-time event dispatching, and it allows us to have pretty low latency and not be cluttered by a whole bunch of other functionality. So at this point, it is worth sort of reviewing what the flow of an LLM-based conversation is. If you're not familiar, basically in an LLM conversation, you start with a system prompt, which kind of gives initial instructions to the LLM. This is who you are. This is what kind of response we expect from you and this sort of thing. And then you start with just a user message that then causes the LLM to respond with some kind of assistant message. And then you want to retain every message that happens so that the LLM doesn't forget what happens along the way. So when you have your next user message coming in, you add it to the list of the previous messages you had. And so this sort of alternating user and assistant messages, they build up over time, and that builds your conversation history. And a pair of these user and assistant messages is what we call a turn. So let's look at how this actually works inside of Cortex. So as I mentioned, Cortex doesn't actually own a database, but it does keep memory of the conversation as it's going. It sends fire and forget messages to persist the history so that we can analyze it later. But basically, like I mentioned, we have this state that is long running for the duration of the WebSocket connection, the client call. We receive audio streams that we send to the speech-to-text provider. And we have all of these events that we're essentially merging into one big event stream. And those events then get combined with the previous state to generate a new state, the next state. And after that new state has been generated, we can then perform the side effects, which you see here. The side effects include forwarding that next event to the next stage in the pipeline. So if you have a user transcription, now we're forwarding it to the LLM to generate the response. So this is the architecture I came up with. I feel like there's a different way you could possibly do this, that maybe, I don't know, you could have the streams cascading into each other somehow, but didn't really figure that out. But I also feel like this makes a lot more sense to me intuitively. The event stream and the state machine is very similar to Redux. If you've seen a reducer before, you kind of know what's in there. It's a big switch case statement that returns the new state. So it made sense to me. So this is what that looks like in code. This is basically the main loop of a call. We have all these streams, the speech-to-text input, LLM thoughts, text-to-speech input, and so forth. And they're all just streams, and they all get merged together into this big event stream. And then we update the state, like I mentioned, and then we perform the side effects. So there's a lot going on here. I'm going to drill down into the text-to-speech portion. But essentially, what's going on when we generate a response, as I mentioned, we perform side effects after updating the state, and this is what that looks like. It's very imperative looking, right? You get the event, and then you grab the service that owns whatever next thing, and then you simply send the event into that service, or you invoke the method that needs to be invoked, and this is what that looks like. But getting back to the mouth, there's a pattern here that I found really useful, that I think it was Yuval Dotner and or Tim Smart helped me figure this out, and became super helpful here, because one of the things that we need to do when the bot is talking and the user starts talking over the bot, we call that an interruption. And when that happens, we want to make the bot stop talking immediately. The bot should not continue talking when the user is trying to say something, right? So it's not enough to just continue generating the audio, keep doing what it was doing until it's done. No, we need to interrupt. And so this is the pattern that we came up with for this. It's something that I'm calling imperative stream. I don't know if this is gonna stick or not, but that's what it is. We have a main stream that is called listen, which is essentially where the action happens, where events coming in from the text-to-speech WebSocket are received and they're forwarded on. And then we have a set of imperative-like methods, flush, interrupt, speak, and so forth, that essentially are really simple. As you can see, all they do is they add items to various queues that are in the mouth service. And that's it. And then those queues in turn are merged into a stream that is part of the listen stream. One of the things that was really interesting here was the interrupt pattern, where we had the stop talking queue, and we are offering a take, and the take type was something that was new to me, where it is a failing take with an error, but then we catch the error, and we'll see that in a minute, but the error causes something to happen with the effect platform WebSocket that is incredibly interesting. Essentially, if the WebSocket fails, with effect WebSocket, it actually will properly close the WebSocket, but then if you add a retry in the stream, it will reopen it, which is exactly what we want to have happen. When we send one of these interruptions, we want to properly and immediately close the WebSocket, but then we want to immediately reopen it so that we have the opportunity to send new messages to the WebSocket. So I thought that was really interesting. And then this is what the listen stream looks like. Again, there's a lot going on here, so let me break it down a little bit. This is the first bit. It's merging the various queues that we just saw, starting with the stop talking queue, and then we flatten the take, and then we're merging the other kinds of streams that we're sending to our text-to-speech socket. And then for all of these, we're just flat mapping them into, and encoding our schema here, which is using effect schema. And then this is really where the magic happens, I think. We're doing kind of what I think Ethan was talking about earlier, turning the stream, turning the WebSocket into a channel, and then turning the channel into a stream, and that allows us to have a duplex stream. We can send messages from the upstream out through the WebSocket, and then also at the same time get new messages from that same WebSocket connection, all in the same stream, which I think is really cool. But as you see here, we have a span, we have the retry forever, while the input is a stop talking error. This reads so incredibly clean to me. I understand exactly what's going on here, and it just works. It just does what it says. And then we also just want to repeat it, forever, if until the actual app is torn down. And that's basically it. We would repeat it, by the way. We need to actually close the WebSocket for reasons at the end of an LLM response generation, and then we want the WebSocket to reopen after that. But that is not an error, that's not an interruption, it's just a finish doing what you're doing, and then close and reopen. So lastly, we're handling all of the incoming messages. This is a little bit more what you would expect to see, but as you can see, we're just, we're decoding, we're filtering out, we're mapping errors that are from the WebSocket protocol, from the TTS service, into effect errors that we then handle, and sending it out through the stream. And that's pretty much it for that. If you have any questions, come at me later. I think there's a lot there. Also, I think as Dylan was saying earlier, we have a lot of errors in our system. We have 27 at my last count of just domain-specific errors, and we also have a bunch of parse errors. We have config errors. We have other kinds of errors that come for free from effect, and we find this incredibly useful. Every one of these errors has specific information or context that helps give users information. It helps with recoverability. It helps with observability. And we have, our own protocol of closure codes that we can send up to the clients that indicate different kinds of errors. And every one of those 27 errors has its own distinct code. So when a user sees a dialog, oh, we had an error, the connection closed unexpectedly, here's the code, it's a 4-digit code. We know exactly what it is. This is just a system that I came up with. It's kind of loosely based on HTTP status codes or WebSocket closure codes, but it's specific to Cortex. But having this system of codes where every error has its own unique code is incredibly helpful. I want to talk about telemetry a little bit because time to first sound is one of our main metrics. So rather than normal HTTP server events where you start with a request from the client and end with a response on the client, we have a lot of server sent events. And so we actually have to track what's going on from a span that starts on the server and then ends somewhere on the client. And so this makes things quite complicated. But essentially, it looks like this. When we break it down, we have a turn. The user speech is usually pretty brief because we only get, sometimes we only get like one message from the speech to text service that says that the user has spoken. But then what we're really interested in is from that moment when we get a transcription, how long does it take for the user to hear a response? And that's what we call time to first sound. And so a lot of that time, as you can see, is spent in the LLM at various stages in the LLM. And so we're able to break that down. And then again, in the text-to-speech, when the bot is actually speaking, the response. This is incredibly bespoke. And what we're doing here is not really measuring the span of a duration like a span of an effect or the span of a function call or an operation in itself, but rather event to event. Because Cortex isn't doing the work, remember, it isn't really accurate to have an effect where, okay, we have a transcript and now we have a response. It's all a stream. So we have to measure event to event within the stream. And so we have kind of a bespoke protocol here. This is what that looks like. Again, a switch case statement. And we have these spans that are kept around on the context. We have logic, depending on the event, to start or stop or annotate the spans as appropriate. And so we came up with our own little imperative system here. This is what's actually under the hood there. It's a bunch of, kind of CRUD methods around spans. But they're basically, as you can see, there's scope refs that wrap a span. And so if the scope were to close, it would end the span. But we're not really using the scoped nature as fully as we could. I think there's some room for improvement here. This is kind of just what we came up with. It's not exactly what effect telemetry was designed for, and it's also not really what open telemetry was designed for. And there's not necessarily a lot of precedent for using telemetry in this way, but we get a lot of value out of it. So this is something I'm still brainstorming how to improve. Now, testing, we've got a lot of tests. We've got, a lot of unit tests, a lot of API tests. And this has also been really important as we make changes and add features to keep things from breaking. I have been a huge fan of testing in the browser, testing TypeScript at various levels for a long time. And so, as you know from the testing pyramid, quick refresher, the vast majority of your tests should be unit tests, and then you have a much smaller set of API tests. And so we have both kinds of tests for Cortex. The unit tests actually use Jest. I didn't have time to get familiar with Vite or VTest. I would like to do that. I would like to try it again. But just in case you were wondering, if you're using Jest and you want to incrementally adopt effects, it totally works. You just need to do a run promise in your test body, and then everything just works as you would expect, essentially. If you have a failure, you get a normal Jest-looking failure message. And And you can do all kinds of effecty things in there. You can use test clock, .adjust, and all of the other goodness that we saw earlier today from the testing talk, which I thought was really cool. And then this is an API test. This is essentially a black box test on the whole service. We spin it up as a web server on port 0, which causes the operating system to allocate it to a random free port, which helps in order to parallelize if you're doing a bigger test run, or if you have a running web server or something like that. It helps to just kind of put it on a random free port so you don't have to worry about stomping on anything. But then we're just driving it through normal API calls the same way a client would, and just asserting on the responses. There's nothing effecty here outside of just like launching the app. But I mean, you could write it effectively if you wanted to, but it's not necessary. It just kind of works this way. I'm a big fan also of mock service worker. I use mock service worker for our backend, for mocking out our backend services a lot. I could understand wanting to also do that by having a mock layer in your test, or mocking a service in the test, and that's also a valid way to do it. But for me, I feel better about refactoring if I just mock the endpoints of the system, the edges of the system, and I find doing that with mock service worker is really valuable. Anyway, that's really all I had. The next steps here are, I'm going to go back to MasterClass and take what I've learned from this conference and see where else we can apply that. I think there's some opportunities to refactor. It may also be that in 6 to 12 months, they come up with a really great duplex LLM AI voice chat model that completely makes this obsolete. And that's fine with me. If it works better, we should be using it. But this is the best thing that we found up to this point. So thank you for listening. I really appreciate it. And thanks again to the community. I couldn't have done it without everybody's help in the community. Thank you.